দেখে কিছু রেসপন্স করি। Stop your mic. Someone has joined from outside. Now we can start. Hello. Hello. Are you hear me?
Yes,
Hello?
sir.
Yes,
Okay.
sir.
Okay. So already 5 minutes late we are. So today we will start with the second chapter in organic chemistry, and in this chapter that is that one is actually the spectroscopy, and spectroscopy that have the syllabus, and that is actually that have to complete within the 2 lectures online. And today we will just say you about the spectroscopy. So why we are interested about this chapter? You will ask me, sir, we are going to be a engineer, so why will read? But this is the subject which is actually required for everyone, means for the those who are from basic science, engineering, medical science, or other material science, or other group of people. So each and everyone require this spectroscopy for characterization of the compounds, characterization of the compounds. So don't try to avoid this chapter, but you have to learn whether you are going to be in electrical engineering, mechanical, civil, computer science, or electronics. Each and every students that have to take the help of spectroscopy for analyzing your materials. And now I will ask you, do you have idea about the spectroscopy? By which subjects is known as spectroscopy? Anyone can say? Hello? What do you mean by spectroscopy? Hello? Hello? No response. Actually, spectroscopy is a subject which deals with the interaction of light with matter. And from there we get some information, scientific information, and that helps to actually characterize the compound. So if a new compound is synthesized in laboratory or extracted from any plant source or animal source, if you have to know the structure, actually without knowing the structure, if you say the different properties, electrical property, its bioactivity, or its conductivity, its semiconductor property, so that is meaningless. So you must have to know the structure. So to actually elucidate the structure, spectroscopy is a helpful subject, and without spectroscopy it is almost impossible, almost impossible. And before going in details about the spectroscopy, I will say you the advantages of the spectroscopy over the different traditional analysis method. Actually, before 50 years or 70 years before, actually different analytical methods generally followed in laboratory for analysis of the compound. Suppose one ore that is collected from any mines, what is their composition, which metals are there, and what percentage is there. If you have to analyze, then it will take near about 1 month in laboratory, and huge amount of manpower, huge amount of reagents, huge large actually long time is required. for analysis. And there some manual error might be possible. Actually, possible means actually error will be there. So that will be not too accurate method. What the results get after 1 month, after long effort, that will be not exact or correct analysis, might be. But that depends on the expertise of the handling person. But spectroscopy actually that make it easy. That make it easy by means of actually very limited amount of sample, very limited within suppose 10 milligram. 10 milligram sample is sufficient for particular analysis. And secondly, this amount of this analysis is not time consuming. At the same time, this sample is recoverable. When you are collecting certain amount of compounds that you have to, when you are analyzing, that is not recoverable, not recoverable. If you have to recover, so analytical method is not a suitable methods. But in spectroscopy, the compound is recoverable, and very limited amount of sample is required. Time is less required and more accurate, more accurate. But the spectroscopy, these instruments are too costly, too costly. Just I will say UV visible spectroscopy, which I will discuss today. Now in my laboratory, the students are working. I will show you that near about 10 to 12 lakhs spectroscopy. But we have in our laboratory for BTech student for doing their practical, that is within 2 lakhs or 2.5. So that is for laboratory purpose. But for a research purpose, it is too costly. Similarly, NMR spectroscopy, NMR mass, that is more than 235 crore. So it is too costly, and more precisely we can measure. So this is all about the advantage and disadvantage of the spectroscopy. And what do you mean by spectroscopy? Already I told you. Now, what I told you, that is written here. That is written here. And in chemistry, spectroscopy play an important role for determination of structure of the molecules. Already I told you. Spectroscopy is the study of interaction with energy with matter. I told you in the definition. When energy is applied to the matter, it can be absorbed or emitted. Just about these things, I will say you few words. Suppose few molecules are floating into the closed vessel, into a closed vessel at a particular temperature, and the molecules are randomly actually translated from one place to another within the bulk of the space. Now, if you use certain amount of energy or you increase the temperature, then what happens? Actually, their randomness will be increased. Their randomness will be increased. Means translational motion increase. Translational motion increase. If you increase more energy to the molecules, then what happens? Actually, that will try to rotate the molecule with different degrees of freedom. Suppose you consider a ammonia molecule. So that molecule in different actually degrees of freedom, it can rotate. It can rotate. Okay, with a particular energy absorbance. And if you supply more energy than that, which cause the actually rotation, actually what happened? Within the compound, the different bonds, particularly sigma bond and pi bonds, actually within the compounds of any organic compound, either sigma bond, pi bond, or in complex compound, coordinate bonds are there. So the bonds within the atoms in the molecule, that we know
Sir, your voice is lagging.
now it's okay. No one is responding.
Yes, sir.
Hello. Okay. When we supply more energy, yes, actually the bonds we consider as two atoms are attached through spring. Okay. Okay. Actually, two balls if connected through a spring, and if you apply some force between two balls, actually sphere, that might be actually the bonds will be expand or contraction, expansion or contraction that will happen. So if you supply energy with that bond, so that expansion and contraction that will so as we increase more energy, that will actually increase in such a way. What high amount of expansion is actually break as a cleavage pathway or heterolytic. In homolytic that generates two radical, and heterolytic carbocation or carbanion or such type of actual dissociation ions that actually generates. So this is the fact. But when we supply more energy than that, then what happened? So within the bonds, actually the electrons actually that remain in their molecular orbital, bonding orbitals, actually two atomic orbitals, suppose two hydrogen atoms, they are one s orbital, when combined that gives two molecular orbital. One is the lower energy, that is the bonding energy, another is the higher energy, that is the anti-bonding. So in bonding, the electrons remain in the bonding orbital. So energy is supplied, then electron from the bonding to anti-bonding that can be promoted. That can be promoted. So this is the fact. If you supply energy, then it will happen. So today we will discuss about the electronic spectroscopy. That is the UV visible spectroscopy. Electronic spectroscopy that actually excites the electron from bonding orbital, bonding to anti-bonding or bonding to anti-bonding orbitals. And that is actually measured by means of UV spectroscopy, by means of UV spectroscopy. And about the staging of bonds, actually the contraction and expansion, what I told you, that is the staging of bond. That is that subject is by the by higher spectroscopy. That also we have our discuss on the absorption. Hello. 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 Hello.
Sorry.
Your voice is breaking.
Voice is breaking. This is the problem of internet in our department. Okay. I'm nothing to do more than that. Actually, I have taken the microphone in front of my mouth. Now it is okay. Voice is okay. Hello.
Yes, sir. Not
Yes, sir. Yes, sir. Now, okay, sir.
Actually, time to time, it is actually the internet that is the weakness or that actually happened. Okay. So what I told you about the spectroscopy, the basic idea that it is clear to all of you. I have to repeat it. Hello. No one is responding. Hello.
Sir.
Bolo. Hello.
Yes, sir.
Hello. Okay. So this is the fact what happened when energy is supplied to the molecules or atoms or the matter. Okay, so now we will say the few words that is very important. That is, in spectroscopy, energy is supplied in the form of electromagnetic radiation. I think all you know actually light that have the two property, particle nature as well as wave nature. So when it propagates through space, that actually one component, that two vectors are there. One is the electromagnetic vector and electric vector, another is the magnetic vector, and these are the perpendicular to each other, and that interact. That energy when it's actually collide, that actually simultaneously collide at a point, that actually emits energy, and that energy absorbed by the molecule. Okay, so that is written here, which has been which has properties of both the wave and particle according to quantum mechanics. Electromagnetic radiation can be described as a wave occurring simultaneously in electric and magnetic field, and it also can describe as it is consist of the particle means that is considered as a photon, means that is the quanta, that is the small packet space. It is different phenomena happen. Different phenomena happen, whether it will be the electric vibration or bending type of. Okay, so this is the preliminary way theory about the light is to explain. You have energy associated with light uh, gamma ray is the it's the reactive decay.
Sir, your voice is breaking.
We can't understand anything.
Yes, sir, it's breaking.
Sir, you are not audible.
And it is penetrating our body that hello hello, it's okay.
Yes, sir, now you're audible.
Hello.
Sir, your voice is breaking so
Okay.
much.
So
So many times.
this is the wavelength range. The wave. So many times is problem of internet in the. Okay. It is not controlled by me. Okay. I'm trying to give you the better service. Just a minute. First I leave, then again I will join. Okay.
Okay, sir.
Okay, sir.
It's now okay. Now hear me.
Yes.
Okay. So yes. Yes. So this is the X-ray range, that is the 10 to the power minus 12 to 10 to the power minus 10, and this is utilized for actually to detect the fracture of our bone. Actually, X-ray, not only that, for for taking the radio analysis, radiologists that take the different X-ray structure of our heart, of our lungs, and different organs nowadays. So that is very helpful. And the next part, that is the 10 to the power minus 8 to 10 to the power. Actually, it should be 10 to the power minus 6, but it should be actually 200 to 800 nanometer. Actually, that is better to explain that to 200 to 10 to the to 800 nanometer. That is actually UV visible zone. But 400 at 200 to 400, that is the UV zone, and 400 to 800, that is the visible zone. So this is the visible. You see here, that is actually started from 376 to 780. But actually, to remember, to make it easier to remember, we say it is the 400 to 800. Okay, so this is the visible. And beyond that one, that is actually infrared. And infrared, that is expressed in terms of wave number, that is 1 by lambda, that is the wave number that we will express in case of infrared spectroscopy. And beyond that one, that is the radar, and this is the FM, TV, short wave, and all these things. Actually, this is for our broadcasting purpose that is used. So this is the total electromagnetic spectrum. We are now interested about our UV visible and infrared, that we have to learn this zone. Okay, that is from 200 nanometer to 800, that is the UV visible. And in terms of actual wave number, that is 4000 to 400 centimeter inverse, that is actually infrared, that will actually we read in our UV visible and IR spectroscopy. Now I will say you what do you mean by spectrum. What is spectrum? Spectrum is the graphical plot of absorbance versus wavelength. This is the
Sir,
UV
please
visible.
share the screen.
Screen is not sharing.
No,
No,
sir.
sir.
Oh, so you say me. No. Yes. Actually, you not inform me. Yes, now it is visible. Hello.
Yes, sir.
Okay, okay. So this is the this is the visible spectra. This is the visible spectra. It is within the range of visible 400 to 800. Means here it is written 400 to 700. Actually, chlorophyll A and chlorophyll B, their structural difference have a structural difference, and that can be identified by means of UV visible spectra. So blue is the chlorophyll A, their lambda max value, and that have the 2 lambda max value at near about 680, and another is around 430. Okay, this blue one is the for chlorophyll 1, red one is the chlorophyll B. So as their structure are different, their peaks are different. So these peaks are very significant and characteristics of the compound, and that appear in the spectrum. And by observing the peak position at which lambda nanometer wavelength in terms of nanometer. So 400 to 800, this is the visible, but UV visible spectrum, actually the instrument all we have, that is the UV visible spectrophotometer, that have the 200 to 800 nanometer. 200 to 800 nanometer. And what is absorbance? Absorbance is the amount of energy absorbed by the molecule. So when any light is irradiated into the solution, into the compound of a solution, certain portion of the light that is absorbed, and this absorbed energy what absorbed by the compound, but compound keep in which way? Already I told you, either the compound utilize this one for rotational, translational, vibration, or electronic transition. Beyond that one, it will be actually transmitted. That will be transmitted. So 100 minus absorbance, that is the transmission. That is the transmission. I will explain it later on. So this plot of the absorbance versus wavelength, that is known as spectrum. So such graph is known as spectrum. It is written here. The instrument by means of which we measure this one, that is known as spectrophotometer. That is known as spectrophotometer. Just in my laboratory, you can see this one. We have a spectrophotometer. Students are working. You see in front of that one computer is just attached with that one, and one invisible spectrophotometer we have for research purpose. So that is cost near about 10 lakhs already I told you. So this is the very sophisticated instrument for research purpose, and already this chart already I have explained about the spectroscopy as well as the absorption and emission. Absorb means the amount of energy which is absorbed, and remaining, that is the emitted. That is the emitted. So absorbance might be either atomic or molecular spectroscopy. So in case of atom and hydrogen spectrum, I think all you know, that is the absorption atomic spectrum. And in case of molecules, means chlorophyll A and chlorophyll B, that is a complicated, a giant molecule, macromolecule. So that is actually molecular spectroscopy. Okay. Now this is the range. Already I told you the which amount of energy is required for UV visible spectroscopy, that is more, because it actually excites the electrons. So when large amount large amount means actually energy corresponding wave is more, then UV visible spectrum that actually responds. So that is written few word sentences here. When an electromagnetic wave is allowed to pass through a molecule, energy is absorbed. After absorption of the energy by the molecule is excited and promoted to the higher level, and these are two types of molecular excitation. Already I told you. Electronic transition, that is excitation. The excitation required generally 15 to 150 kilocalorie per mole. So that is for your UV visible spectroscopy. And this energy is available from the UV zone. From the UV zone, when absorption of energy from the UV region is considered, the spectroscopy is known as UV visual spectroscopy. Molecular vibration excitation also occur. Already I told you the molecules vibrate, their bonds that vibrates in different dimensions, different freedom. So that energy is comparatively less. That energy is comparatively less. So 1 to 15 kilocalorie per mole energy required for the infrared spectroscopy. For infrared spectroscopy. So uniqueness of the spectroscopy, the amount of light energy absorbed by the molecule is the characteristic feature. Always remember, this is the very specific that absorb of a particular compound that amount of energy, and it show a particular peak that is known as actually lambda max. Lambda max means actually absorbance maximum, and that become a peak. That is actually very characteristics. We say it is the signature of the compound. Each and every person that have a specific signature, and each and every compounds their spectrum is also we say as a signature. So this is very unique. And apart from this UV visible, different spectroscopy are used for research purpose. That is the UV, IR, NMR, EPR, Raman, Mossbauer, and mass spectroscopy. So different spectroscopy that we have, but all these are not included in our syllabus. Only for the flavor, the subject, only UV visible and IR are included for your syllabus. Now, this is the absorption spectroscopy, what I already explained, that is written here. Absorbance means amount of energy if you supply to the molecule that will absorb. And if it is in the range of UV visible range, then electronic transition occur. You see here, this is the ground state electronic level. So from the ground to excited state, it excited when it's absorbed energy. And the electrons go to the higher energy, and it is the metastable step. For a time means it will be there, then again it will be returned. So this amount of energy absorbed, that is actually quantized, and it is measured by means of UV spectroscopy. And two terms you have to remember: the power, the energy of the beam is reaches in a particular area. Actually, this is the indirectly we say it is the intensity, power per unit solid angles. So power and intensity are different. I think intensity the amount of quanta per square area, and power means actually number of actually quanta. Okay, but energy, when it is the different, that is the power. Okay, so these are the two terms you have to remember. And UV visible spectroscopy, that is actually the based on two law. Two law are associated with the UV visible spectroscopy, that is the Lambert's law and Beer's law, and combinedly it is known as Lambert-Beer's law. And Lambert-Beer's law, that is their mathematical expression form is the A equals to epsilon L into C. What is A, what is epsilon, what is L, and what is C? It is very important. A is the absorbance, what we observe in y-axis of the UV visible spectrum. And epsilon is the characteristics of the compound. This is the absorptivity constant. Actually, Lambert's law, that is the absorbance is proportional to the wavelength, is proportional to the path length of the solution or media. Okay, you see here, if you keep your solution within the 1 centimeter square cuvette. Actually, generally the sample we have to take in 1 centimeter cuvette. So that is the path length L. If you increase the path length, then more amount of energy will be absorbed. So that is actually interrelated. And again, if the concentration is the more, then absorbance will be the more. So that is the Beer's law. So Lambert's law is the amount of energy absorbed by the molecule is proportional to the path length of the sample, as well as absorbance is proportional to the concentration of the solution, that is known as Beer's law. And to this mathematical form A proportional to L, and A proportional to C, if we combine and if you have to remove the proportionality sign, then you have to multiply by a constant, that is epsilon. This is known as absorptivity, and this absorptivity, actually this is the characteristics of the compound, of a particular compound. This is the characteristics due to their different bonding, bond angles, different number of atoms, their attachment, so many things. So this is the Lambert-Beer's law, and based on this Lambert-Beer's law, actually we use spectroscopy that actually designed and also we utilize for the analysis of the compounds. So this is the fact you see here, P0 the power intensity of the light that actually entering into the solution after when it is actually exit, means actually when it is just coming out from the solution, it P become P, P0 become P. So P is P0 is greater than P. So actually the intensity that actually reduced and that is absorbed. The P0 minus P, that is absorbed by the compounds. So this is the two terms, that is the transmission. T is the equals to P by P0. That is actually ratio of the intensity power. That is P0 by P by P0, percentage of transmission, that is for 100. If we multiply that one, then it is 100% transmission. So this relation has been established in terms of absorbance, that is log 10 base P0 by P, that is the absorbance A. So absorbance, what we plot in x-axis, that is the log 10 base P0 by P. So that is the P0 and P, that is the amount of energy that entering, and after coming out from the solution, actually amount energy remaining. So that is actually proportional. And this is the actually spectrum of KMnO4 solution. You see here when the transmission is more, actually this is one is the complementary of the other. When the transmission is more, absorbance is less. You see here the first one, that is the absorbance is the less, absorbance is the less, and when it is the transmission is the less, absorbance is the high, absorbance is the high. And so this is the interrelated one. If it is the more, then other will be the less. So this is the different relation. Already I told you, absorbance is the log 10 base P0 by P, that is equal to minus log 10 base T, means that T is the transmission. And this is the this relation, actually the Lambert-Beer's law is valid at a particular concentration. So this is the further it is written, A equals to absorbance equals to epsilon Al into C equals to minus log 10 base T by 100. So epsilon is the molecular absorptivity compound at a given wavelength, and its unit is the liter per mole per centimeter. L is the path length. It is generally taken 1 centimeter, but for different research purpose, it might be the less than 1 centimeter or might be the more, depending on our requirements. And C is the concentration, and concentration of the solution that should be the very less. So less concentrated compound gives the more accurate result. So if you take more concentrated solution, then it deviated from the Lambert-Beer's law, that is actually shown here. Absorbance that become a straight line at a particular concentration, and beyond that one it become actually curved nature, means it is invalid. So at a particular low concentration, so at low concentration it actually absorbance versus concentration, that is proportional, but after that one the proportionality lost. Okay, so at low concentration it gives the more accurate result. So what I told you, it is written here, not necessary to explain the terms again, already I told you. And deviation. So deviation, what I told you, it is written further because to explain when you are conducting any, when we are measuring the absorbance, at that time if any reaction occur, then absorptivity will be different, as well as their lambda max will change. So dichromate in water, that from the chromate, so the structure as it is changed, so their absorptivity will be changed, so that deviated from the Lambert's law. Lambert and Beer's law, and this is deviated from related with the concentration. So chemical reaction as well as the high concentration that actually deviate from the Lambert's law. So you have to consider the reactions which actually when we are measuring the absorbance, then no reaction should be changed, followed, or should be occur, as well as the low concentration we have to prepare the solution. Now I will already I told you actually two types of spectrophotometer are available in market. One is the very costly that is used for research purpose, and another was comparatively cheaper for actually practical purpose for actually for the student. So their accuracy is very important. Actually more accurate one is that actually differ 1 centimeter, 1 nanometer difference or 2 nanometer within that difference, but a cheaper one that actually deviate quite from the accurate measurement. Now this is the few words again I have to repeat, already told you that is in UV visible spectroscopy electronic transitions takes place, already told you, and light from the UV region is allowed to pass through the solution of the compound under investigation. Already I told you, and wavelength range of UV visible that is 200 to 800 nanometer that correspond to 15 to 150 kilocalorie per mole. Already told you, not necessary to repeat. After absorbance of UV light, electronic transition occur. Okay, so all these are already informed, already explained. Now this is the actually molecular orbital and their probable excitation probability. So in a molecule, what I told you, either sigma bonds or pi bonds are there. So sigma bond that have two orbitals, sigma molecular orbit, one is the sigma bonding and the sigma anti-bonding. Similarly, pi have also pi bonding and pi anti-bonding, and N is the non-bonding. Actually non-bonding means the lone pair, when it resides within a molecule at a particular atom. Suppose in ammonia one lone pair is there, in water molecule two lone pairs are there. In case of chlorine molecule 6 lone pairs are there. So that is actually non-bonding electrons. That is the non-bonding electrons. So within the compound, the different electronic position in the different bonds are in their molecular orbital. So when large amount of energy is supplied for electronic transition, so electronic transition which are possible to in which range to which orbitals that is possible, that is written here. So sigma correspond to sigma star, have pi to pi star, n to pi star, but depending on their energy gap actually that actually allowed, that is allowed, but other are forbidden. Forbidden means actually not allowed. And now you see here, this is the actually potential diagram, actually level of energy of the different orbitals. This is the sigma orbital, that is the lower energy. This is the pi, this is the non-bonding. This is the pi anti-bonding. This is the sigma anti-bonding. So you let me know from sigma to sigma star is allowed, or from pi to pi star is allowed. Which one will be allowed more? Hello? Hello? Are you hear me?
Sir, repeat again once.
Actually, which transition from sigma to sigma star and pi to pi star, which is more easily allowed?
Sir, pi to pi star.
Yes, very good. Pi to pi star means it is the lower energy. Okay, their energy gap is less. Similarly, n to sigma star or n to sigma pi star, these are comparatively less energy. So these are the actually different possible transitions that occur within the compound depending on your amount of energy supplied, and it gives the information about the presence of pi bonds or non-bonding electrons and other informations. Is any conjugation is there or not, or some actually functional groups, nitro group, nitroso group, aldehyde, ketone, group are there or not, that we can identify by means of this spectroscopic method. So transition will occur only when maximum amount of energy that is required for transition is supplied. In other words, the transition will occur at a particular wavelength denoted by lambda max. Okay, lambda max is the where it is the maximum electron transition occur at which length of the energy corresponding at a particular wavelength. So that is the very characteristics of a particular compound. So depending on that, different transitions that occur either into pi star, into sigma star, or pi to pi star. So when a hydrocarbons are there, that means methane, ethane, propane, butanes are like, so there are sigma bonds and sigma stars are there. So that will generally show its peak near about 200 nanometer. 200 nanometer. Now the nature of electrons means the functional nature. That means whether it is attached, associated with the sigma bond, pi bond, or non-bonding, or within a certain functional group, that we can identify. So what I told you, that is the basic concept about the spectroscopy. Now I will say you few terms. Always remember, each and every subject have a specific terms, because these terms you have to learn, because each yes, actually each and every subject have the specific term, like in medical science, in physics, in chemistry, in biology, in history, each and every subject, that terms you have to know, otherwise it is very difficult to understand the subject. Now we will explain about the chromophore. What is chromophore? Chromophore is a color imparting group. So when a functional group is introduced within the structural moiety, when it imparts color, that is known as chromophore. So nitro group, OH group, nitro group, actually that is chromophore. I will say you it is the chromophore. So thus chromophore may be defined as isolated multiple bonded functional groups which have characteristics irreversible absorption property. And compounds containing chromophoric groups are known as chromogen. The compounds which have the chromophoric group, that is chromogen. And characteristic features of the chromophore, that actually absorb at a particular wavelength that lights, and it show its particular wavelength in the visible spectrum in the spectrum. So a particular chromophore present in different compound will absorb visible light at a particular range of wavelength. Different chromophores will have different lambda max. A particular chromophore present in different molecules may different chromophores, so that will be different, but intensity of UV light, that will differ. So this is the characteristics of the chromophore. And now this is the more important, a few important terms that I have to explain. That is the intensity, means the absorption, how much amount energy absorbed at a particular wavelength, that actually related to the Lambert-Beer's law, and according to that one, actually we can measure. And here the absorptivity or extinction coefficient lambda, that is very epsilon, that is very important, and it is actually characteristics of the compound, already I have explained. So from the value of the epsilon, we can have an idea regarding the intensity of the light absorbed, means which type of functional group is there. Again, epsilon has been found to be related with the probability of transition as epsilon, that is 0.87 into 10 to the power 10 into P into A. What is P? P is the probability density of probability of the excitation, and A is the area of the target, means the functional group present within the compound. So these are the different terms that is very requirements to understand this subject. Now the value epsilon can get the following two information: intensity of the light absorbed, as well as the same thing what I told you, and some important chromophoric groups, that is the nitroso, azo, amino, carbonyl, paraquinone, orthoquinone. So these are very specific functional groups that actually that can be easily identified by means of light fan দাও তো, ফ্যানটা একটু দিয়ে দাও তো, ফ্যান Next, the term is the oxochrome. What is oxochrome? Oxochrome, the functional group which actually impart color within a particular compound. Actually, oxochrome, oxochrome. Actually, that yes, that actually enhance the intensity. Enhance the intensity of the color. That is the oxochrome. Suppose benzene. I think all you know benzene is colorless. Benzene is colorless. When you introduce one nitro group in the benzene, then it becomes nitrobenzene, and nitrobenzene quite pale yellow color. So benzene is the colorless liquid, but nitrobenzene also liquid, but when one OH group is introduced into the nitrobenzene, suppose ortho paranitrophenol, then it is your so OH group is color, imparting color imparting property. So saturated groups which when attached to the chromophore alter both the wavelength as well as the intensity of the itself do not absorb, but in presence of this food is the absorbance intensity. Actually, it should not be like that. Benzene is not a chromophoric group, but when nitro group is introduced, okay, and when it is one OH group is there, then intensity is changed from 150 to 275. So these are the different functional groups that actually behaves such type of characteristics. And this is the nitrobenzene, that is 270 nanometer. That so its lambda max value. Next, the bathochromic shift or red shift. Actually, the spectroscopy, that is a harm type of spectrum that show, but this lambda max position, if it is shifted towards the right, means that actually from higher wavelength, then it is known as the bathochromic shift or red shift. When it is the shifted towards the left, that is known as the blue shift. That is known as hypsochromic shift. Hypsochromic shift. So this is actually we have to correct this one. Actually, aniline that show 270 nanometer its wavelength, whereas its protonated aniline that's 275. So this is the hypsochromic means actually when absorbance become more, when absorbance is more, or when it is decreased, that is the hypsochromic. When it is the absorbance quite decreased in presence of some functional groups or some removal of some functional group, that is known as hypsochromic. So these are the very specific term which is used in the individual spectroscopy, and these are the different parameters which are related with the chromophore. Chromophore. So from the relation of epsilon, that is 0.87 into 10 to the power 20 into P into A, where A is the target area. A is the target area. That is the size of the chromophore. It may be concluded that transition or intensity of the UV light depends upon the size of the chromophore. Whether it is the chromophore means it is the conjugated or non-conjugated. You see here, this is the non-conjugated system. Its absorbance that is at the lower wavelength. But when it is the conjugated, it will appear at the higher conjugation. So it is conjugated or non-conjugated that we can easily identify by means of this spectroscopic information. So that is why the conjugation chromophore absorb UV light more readily than the isolated chromophore. Since UV energy is quantized, so certain amount of energy that actually absorbed, and depending on this amount of energy, depending on the structure of the compounds, we can identify or we can say which one is the more conjugated or less, or the length of conjugation. So this is the different structure you see here. This is the ethylene, So pi electrons, that is the from pi to pi star, their transition energy more. But when it is conjugated with the another double bond, then the gap between the pi to pi star, that actually reduced. So as the conjugation become more, the gap actually reduces, and it actually appear as less amount of energy required. So that will shift from higher wavelength. That will be the bathochromic shift. That will show as a bathochromic shift. Is it clear? So different spectroscopic term which is now not recently used, but these are the old terminology. That is the K band, B band, E band, and R band. K band is the associated with the conjugated system. So when any conjugated systems are there, then K band is observed in the spectroscopy. When it is a benzenoid system is there, then B band is observed that within the particular wavelength that actually appear. So from that peaks, we can say benzenoid systems is present within the compound. E band, that is the if it is appear, then we can say ethylenic double bond is there. Similarly, when N to pi star transition, particularly in case of carbonyl group like that, so R band that appear. So K band, B band, E band, and R band, that actually specify some kinds of compounds from the spectroscopic observations. And these are the applications. Actually, bolo.
Sir, we have class from 12 next class.
Okay, so now I will stop. So next day we will take your class from application of the visual spectroscopy. Okay, so I will leave.
Thank you, thank you.
Do you have any question? Hello? Don't have?